Today, we will look into the core of the MIP solver, the branch-and-bound algorithm. Therefore, we will quickly repeat the idea of branching. And then we will learn about some branching rules: strong branching, pseudo-cost branching, reliability branching, hybrid branching, and cloud branching. And finally, we will also look into node selection rules. So, let's have a look again at our MIP Solver flowchart.
We continue with the next part of this lecture series on MIP Solver components. In this lecture, we will look into the core of the branch-and-bound algorithm and learn about branching rules and node selection rules. Let's start with a short reminder how LP-based branch-and-bound works. First, we select the original problem. We solve the initial relaxation. There are two fractional variables. We branch on one of them. To keep track of the subproblems, we build up a tree data structure. We select one of the two subproblems/nodes to be solved next. We solve the relaxation of this subproblem. This time, there is only one fractional variable. We branch again. We select one of the subproblems. We solve its relaxation. Now we find that the relaxation is integer. We have our first incumbent, and can apply bounding for anything below this line. We select the next node. The relaxation is infeasible. Thus, we can prune this node. We select another node. We solve the relaxation. And we branch, creating two new subproblems. We select one. Solve the relaxation. It is integer feasible. We can update the incumbent. We solve the last node. There are two main decisions that are taken within LP-based branch-and-bound. The first is the node selection. Which subproblem do we consider next? And the second is the variable selection. Which fractional variable do we branch on? Among these two, the variable selection is clearly more important in practice, whereas the node selection mainly determines in which order the tree is processed. The variable selection defines how the tree is built up, how it looks like. A bad selection, for example choosing a variable at the root node which doesn't have any impact on the remaining problems at all, might simply duplicate search effort. Bad variable selection really fires back quickly and should be avoided by all means. This has been known since the very beginning of computation of mixed integer programming. Many researchers have worked on efficient branching rules. Some publications that are still relevant today date back to the 70s, almost 50 years ago. Let's start with a brute force method, which is called strong branching. The typical goal of all branching rules is to improve the dual bound equally in both child nodes. To do so, strong branching simply computes this dual bound. It performs a look ahead by solving all the possible descendants of the current node. It applies the bound change from branching and solves the resulting LP. Consider the example on the slide. For the two fractional variables, strong branching would apply both the up and down change, and then solve the resulting linear program for them and thereby get different objective function values. Then, for each of the two branches that belong to one variable, it would combine the two values to one single measure. At this point, what has been done for many years within MIP solvers is to take a convex sum of the two. Empirical studies showed, however, that a much better heuristic measure to combine these dual bound improvements is taking their product. Strong branching, as you can imagine, is quite expensive with respect to running time, since at each node it solves 2 times the number of fractional variables many LPs. At the same time, it's very effective with respect to the number of nodes. With respect to node count, it is more or less the most effective branching rule that we know. Moreover, strong branching might have a lot of useful side effects. It might change bounds when it finds one of the two sides to be infeasible. For example, after branching on a binary, if one of the strong branches is infeasible, the variable can be fixed to the opposite side. It might even detect infeasibility when both sides are infeasible and then cut off the current node. And, of course, it might also find feasible solutions. There are various ways how to speed up strong branching. It is indeed rarely applied in the pure fashion. First of all, strong branching might be performed only on a few fractional variables, the most promising candidates. We can do a dynamic look ahead. As long as there are frequent updates of the best predicted branching candidate, we continue. But if there is no update for a couple of strong branches in a row, we stop. Another way is to limit the number of simplex iterations, by not solving the strong branching LP to optimality but just perform some iterations, for example 50. A special case is to do only one single iteration, which is, of course, a very cheap thing to do. This is called dry-beak penalties. These penalties can be efficiently computed from the ratio test of the simplex algorithm, and do not require a separate LP solve. One additional suggestion to improve this process is to apply domain propagation before solving the strong branching LPs. This is a form of local pre-solving and leads to better branching predictions. Compare the pictures and the indicated objective levels with the picture 2 slides ago. As an extreme form, one might only apply domain propagation instead of solving strong branching LPs. This will again be a comparably cheap branching rule, even if fully applied to all fractional candidates. One of the most important concepts for branching rules are the so-called pseudo-costs. One could say that strong branching is an a priori observation, since the impact is computed before applying the branching. Vice versa, pseudo-costs are computed a posteriori. Only after solving the resulting subproblem, the observed change in the LP solution quality is computed. Hence, we keep track of this information and thereby build up a history information for each of the variables on which we branched in the past. This gives an estimate of the average objective change observed when branching on certain variables. Then, this can be used for predicting what the change will be in future branches. More precisely, for each node the objective gain per unit fractionality is computed for the variable that led to this node. The variable-wise average of all such observations are the so-called pseudo-costs. In brief, pseudo-costs are the average unit gain taken over all the nodes that have branched on this variable in the past. Consider the lower picture. We see the fractionality of the variable on the x-axis and the objective on the y-axis. The important quantities are the marked angles, rather their tangents. The red point represents the fractional LP solution value, while on the left and right we mark the change in the objective function by delta down and delta up. You get the tangent of the angle is dividing the objective change by the fractionality. Pseudo-costs are averages of such tangents for different LP solutions and objective improvements. Pseudo-cost branching uses these pseudo-costs for taking branching decision. We use the knowledge of the average objective change from a variable to estimate what the change might be in an upcoming branch. Thus, we now start at the current fractional point, marked red again, apply the average angle that we saw historically and predict the delta down and delta up that we assume to see in the potential child nodes when branching on this variable. This is of course much cheaper than computing those values exactly via strong branching. Again, for each of the fractional variable we would get two values, the down prediction and the up prediction. The branching rule looks for a variable that has a large value in both, again by choosing one with a maximal product of the two predicted values. Pseudo-cost branching is at the core of most state-of-the-art branching schemes. It gets better and better during the search. Once more and more history information is collected, the pseudo-costs will get more and more reliable and the predictions will get more and more accurate. That's what we hope for. Unfortunately, however, the most important branching decisions are taken at the beginning of the search. In particular, the one which affects the search most is the very first branching decision taken at the root node. This is where we don't have any pseudo-cost information available. Hence, the idea came up of combining pseudo-cost branching with strong branching. A typical strategy is to use strong branching instead of pseudo-costs when you never branched or strong branched on a variable before. Of course, the values given by strong branching can be treated as if they were past branching observations, hence used to initialize pseudo-costs. It was in 2005 that researchers discovered that it's computationally even better to do strong branching more than once per variable. In other words, a variable is considered unreliable as long as there have been less than k strong branches on it, where typical values for k are something between 4 and 8. Moreover, follow-up publications have shown that it also makes sense to have k depend on the variance of the pseudo-cost values. The logic behind this can be understood in this picture. For the red variable there are only 10 observations, but they're almost the same, hence the average can be considered a safe prediction. Whereas, for the blue one, where there are 16 observations with very high variance, the value to choose to make the next prediction appears unsafe. Other research questions about this are how reliable a strong branching that hits the iteration limit should be considered, and whether we should reconsider strong branching when a subproblem starts to behave differently than expected and pseudo-costs that are used for branching don't match anymore what is observed during the search.
In this lecture, instead of 2 quizzes with 3 questions each, we will have 3 quizzes with 2 questions each. So let's start with the first one. Pseudo-costs are an underestimator for the objective change when pivoting, or B, are an underestimator of the objective change when relaxing a constraint, or C, are an estimate of the objective change when branching. Question number 2, strong branching is very competitive with respect to A, the running time, B, the number of nodes, or C, the prime and dual integral. Quickly think about the answers, and then we will continue with the solutions. So, here we go. First question, pseudo-costs are an estimate of the objective change when branching. And second question, strong branching is very competitive with respect to the number of nodes. So, pseudo-costs are not the only history-based branching rule. There are other rules of this type and also ways to combine them.
Other history-based rules, like inference branching and VSIDS branching, also try to use past observations to estimate, hence maximize, the impact of the current decision. Inference branching was inspired by constraint programming methodologies. It counts the average number of bound reductions that follow from branching on a variable. In the tiny MIP in the example here, fixing x1 at 0 implies 2 things: x2 has to be equal to 1 and z can't be less than 3. So we would say that the inference down score for this branch on this variable is 2. Down branching on x1 triggers 2 bound reductions. Inference branching keeps history information on the number of triggered domain reductions, again for up and down branches on each variable, and aims at selecting a fractional variable that is expected to trigger many deductions on both sides when branched on. Note that this is independent of the actual LP value. Next there is the so-called VSIDS branching, sometimes also referred to as conflict scores. This rule is related to conflict analysis, which is a whole lecture topic of its own. Loosely speaking, conflict analysis is a technique to learn additional constraints when finding an infeasible subproblem during the search. The learned constraint can be seen as an explanation of the infeasibility. It is a single constraint that would have sufficed to trigger the local problem infeasible. The rationale is that such a constraint will help in the remainder of the search to detect infeasibility earlier. VSIDS branching branches on the variable appearing in the largest number of such conflict constraints. In other words, it keeps statistics of how much impact a variable has for triggering local infeasibility. VSIDS is the state-of-the-art branching rule in SAT solving. The idea of hybrid branching is to combine these 3 branching rules into one common branching rule, which uses all of these statistics at the same time. Hybrid branching does a suitable scaling and rating on these 3 statistics, since their values can be on very different orders of magnitude. Thereby, they are combined into a single score. Alternatively, One might use a leveled filtering approach, which consists in sequentially filtering the set of candidates, each time using a different statistic. For example, first consider the 100 candidates for the best inference score. Then, out of those, select 10 candidates which have, this time, the best VSIDS score. Finally, out of these 10, take the one with the best reliability score. To conclude with branching rules, let's talk about cloud branching. Cloud branching tries to address a problem that we observe very often, the problem of dual degeneracy. In many cases there are different optimal solutions. For example, the whole edge of the polytope in the upper picture is optimal, hence there are two different optimal vertices. In particular, in a lower dimensional polyhedron, like a two-dimensional polyhedron in a three-dimensional space, it's very easy to come up with an objective function that has one of the facets as an optimal solution space. The idea of cloud branching is to exploit the knowledge of multiple alternatives of the LP relaxation. The question is, how do we get these extra optimal solutions? First of all, we can easily try to restrict the LP to the optimal face by adding one additional constraint that sets the objective function equal to the value that it has in the optimal LP solution. Then we can explore this optimal face. This could be done either by something like a feasibility pump, using an auxiliary function which tries to point us into different corners of the face, or in a very brute force manner, minimizing and maximizing each of the variables over this optimal face. Such strategies will give us solution intervals for each of the variables instead of one fixed solution value. This is depicted in the lower picture. Assume the polyhedron you see in the picture is the optimal face of a higher dimensional polyhedron, and minimization and maximization is performed for each of the variables. So, out of the 6 possible vertices, this procedure gives 4 different potential optimal solutions, one for each of the 4 different auxiliary LPs, defining an interval for each variable. Hence, for the variable x1 optimal LP solutions exist between 0.4 and 1, while for x2, everything between 0 and 1 is a possible solution value. Thereby, we already know that when branching on x2, we will not observe an objective improvement in either of the child nodes. These intervals can be used in connection with pseudo-cost branching. Firstly, they are taken into account when pseudo-costs are updated. The history statistic is computed at the endpoints of the interval, instead of a single, random LP solution point somewhere on the interval. Clearly, for the same objective changes, this will give larger values than traditional pseudo-costs. Secondly, the endpoints of the intervals are used again when the estimation is made. This will give smaller estimates when the same pseudo-costs were used. One could hope that these two effects cancel out against each other on average, but it can be shown that this is not necessarily the case. Moreover, it was empirically shown that cloud-based pseudo-costs are much better in predicting the actual objective change in the child nodes. A similar procedure can be applied to strong branching. Here, the main benefit of cloud intervals shows up when a fractional variable gets integral in one of the cloud points. In this case, solving the corresponding strong branching LP is not necessary anymore, because it will give a zero objective change. In other words, cloud branching acts as a filter for strong branching. On the other hand, new fractional variables might occur when exploring additional LP optima. This provides new branching candidates, for which one of the strong branching values is already known. This is similar to the idea of non-chimerical branching, which uses values from other strong branches to compute underestimators for strong branches that haven't been performed yet. As already mentioned earlier, most of the branching rules yield 2 values, one for up and one for down branching. These need to be combined into a single value. One option is to take a convex sum of the two, but it is empirically better to use multiplication. Finally, instead of branching on a single variable, one might also branch on general disjunctions. This procedure is also called branching on constraints. As an example shown in the upper picture, one could branch on the constraint x1 plus x2 less than or equal to some integer value, or larger equal that value plus 1. For the polytope depicted in the bottom right side, you see why this can be a good idea. The optimum has only one fractional variable, which consequently will be branched on. Performing such a branching would reproduce a similar situation, an optimum with only one fractional variable in the optimal LP solution. Using a variable-based branching rule, 15 steps are necessary to reach feasibility. At the same time, a simpler constraint branch, such as x1 minus x2 less equals 0, or greater equal 1, as shown in the picture, will give a deep split here and lead to an integer solution just after a single step. General disjunctions are more powerful than single variable branches, but the crucial question is, how to find good general disjunctions to branch on? The answer is that, at the moment, there is no generic scheme that improves the overall MIP performance. Express only uses general disjunctions in some distinct special cases. An idea that is at the intersection of variable-based branching and branching on general disjunction is to branch on multi-aggregated variables. A multi-aggregated variable is a variable that has been replaced by a linear expression in presolving. Hence, the variable is not present anymore, but the information exists which variables have been exchanged by linear expressions. The idea of branching on multi-aggregated variables is to branch on general disjunctions if and only if they correspond to variables that have been multi-aggregated in presolving. The rationale is that those disjunctions represented a decision variable in the model that the user originally created. Also, this overcomes the main problem of general disjunction branching. There are a lot, infinitely many, general disjunctions. Multi-aggregations, however, present a well-defined, typically very small set of additional candidates to enhance the set of branching candidates.
So far for branching rules. Let's continue with our second quiz. First question. Strong branching plus pseudo-cost branching equals A. Cloud branching, B. Reliability branching, or C. Inference branching. Second question. Cloud branching makes use of A. Multiple LP optima, or B. Multiple integer solutions, or C. A combination of LP optima and integer solutions. Do you know the answers? Take a little time, and then we show the solutions. Okay, here we go. Reliability branching is a combination of strong branching and pseudo-cost branching. And cloud branching makes use of multiple LP optima. So, next to selecting the branching entity, the other big choice in Branch&Bound is the selection of the next subproblem to process. This is also called node selection.
Node selection fulfills different purposes. First of all, one goal is to improve the primal bound to enable pruning. In particular, at the beginning of the search, finding feasible solutions is important. Moreover, very importantly, the computational effort should be kept small. Both can be achieved by preferring children over siblings over other nodes, in a depth-first search manner. As an example, if the green node is the current node, the best candidates to continue the search are the two children, marked yellow, the next best is the sibling in light orange. The reason why this leads to low computational effort is the warm start behavior of the dual simplex. A child differs just in a single bound change, we expect very few iterations for the re-optimization. A siblings differs in a bound flip, again, few re-optimizations are expected. The further apart in the tree two nodes are, the more expensive we expect the next LP solve to be. Furthermore, a third goal of node selection is to improve the global dual bound. Finally, in parallelization, it's important to find an efficient node selection strategy, which quickly produces as many open nodes as possible, such that we can ramp up the parallel threads to work on separate parts of the tree. How do typical branch and bound trees actually look like? The tiny examples that we had in this presentation were more or less complete binary trees. As you can imagine, this is not the regular case. Here are some visualizations of actual branch and bound trees produced when a MIP solver solved MIP-lib instances to prove an optimality. Those still come close to the ideal that we might have in mind. They are nicely balanced binary trees, with a characteristic depth level until which the search goes before pruning, maybe with a few outliers. However, it's much more common in practice to have very imbalanced trees like the ones shown here. Pause the video and think about why this is the case. In most cases, branching a variable in one direction has much more consequences than branching it in the other direction. Simply think of a set packing situation, where you have to choose at most one out of n items. Branching one of the variables to 0 means that you will not pick that one single item, and this typically does not have much impact on other decisions. However, branching a variable to 1 implies that all other variables in the constraint have to be 0. Furthermore, the fact that an item has been selected might have further consequences. Now imagine that decision variable appearing in many set packing constraints. The up branch might be a game changer and lead to a very small subproblem to be enumerated, whereas the down branch is only a slight change to the original problem. Such a situation can be seen in the lower picture. The shape of the tree is of course tightly linked to node selection. By the choices of the node selection rule, the tree gets shaped, since it determines where now leaves will be created. At the same time, the tree shape defines what options node selection has to choose the next node from. As a final remark, the two most common cases for practical MIPS are yet not depicted here. The first one is trivial from a branch and bound point of view. MIPS that get solved at the root node. A significant portion of industrial MIP problems falls into that category. That does not imply that those are easy problems. They still might take hours to solve, because of their sheer size with millions of variables and constraints. But their structure is very tight and hence they can be solved purely by means of cutting planes, heuristics, and efficient pre-solving. A second common case is the exact opposite. Small problems that require huge search trees with millions of nodes. Those cannot be easily visualized. Again, you should not expect that those are complete or almost complete trees. If anything, the first few levels might be complete, but most times not even that. The shape of the tree rather consists of a few tens of thousands of paths that do not diversify much, each of them with a depth of a few hundred nodes. This situation is comparable to the first tree on this previous slide, just orders of magnitudes larger. Why is this a common case? The main reason is that MIP solvers do depth-first search for most of the time. Depth-first search always tries to select a child node of the current node. If the current node is infeasible, it will select a sibling. If this is also infeasible, the solver will perform a full backtrack. This behavior is also known as diving or plunging. On the one hand, this is beneficial for finding early feasible solutions, which often can only be found deep in the tree. On the other hand, it minimizes the computational effort, since depth-first search requires the least data structure updates, and is most preferable for warm-starting dual simplex. The question that each MIP solver handles differently is how to combine depth-first search with something else. One strategy is to use breadth-first search in the beginning, to get a big diversification, which is useful for the ramp-up of parallel branch and bound. Two other strategies are best bound search, which chooses the node with the best local dual bound in order to improve this local and thereby also the global dual bound, and best estimate search, which computes an estimate of the best MIP solution in the subtree by using pseudo-costs. Typically, one or both of these strategies will be applied when the solver backtracks, that means, when a dive is finished. Then instead of doing local backtracking, the next node is selected with respect to one of these criteria. Moreover, one might combine them, either by defining a hybrid score or by just alternating them. Finally, there is the idea of UCT node selection for the ramp-up phase. UCT stands for upper confidence intervals applied to trees. It tries to balance exploration and exploitation. UCT aims at going towards nodes that have a good, but not necessarily the best, estimate, and at the same time, along a path that has not been explored much so far. Therefore, it sets in relation the number of times that the parent node and the possibly child node was on the path from the root node to a leaf node and uses this to balance those two different objectives. This is a concept for the beginning of the search, hence only applied to the first few nodes, if at all.
All right, all nodes selected? Then it's time for our final quiz. First question. Most of the times, a MIP solver will select as next node A, a child or sibling of the current node, or B, a node close to the root, or C, a node with the best dual bound. And second question, with respect to running time, node selection empirically has A, a larger impact than the branching rule, or B, a smaller impact than the branching rule, or C, about the same impact as the branching rule. And here are our solutions. Most of the times, a MIP solver will select a child or a sibling as the next node to process. And second question, with respect to running time, node selection has a smaller impact than the branching rule. The branching rule is by far the more important decision. So I hope you liked this lecture. Thank you for your attention. Keep on branching and don't get pruned, and see you for the next lecture. Bye-bye.